We are coming back and revisiting Chapter 7. I'm also pleased to report new microphone. So hopefully the cracking is gone. No more crackling of the microphone. You can actually listen to my voice. You don't have to read the subtitles, the captions, whatever, that are probably wrong a lot of the time. So endothermic and exothermic reactions. The signs of delta H, enthalpy, and delta E are internal energy, change in internal energy, follow the same convention. So we've done a little bit of this before. When delta H, or change in enthalpy, or we can sort of think of it as heat, when that is positive, heat is being absorbed by the system. There is a gain in energy, just like with an increase in delta E. And we call this an endothermic reaction. The endo here meaning going in. When delta H is negative, heat is being released by the system. It is losing energy or emitting energy. And we call that an exothermic reaction, exo meaning out, an outthermic reaction. So heat is being released. Exothermic would be like combustion reactions, where they produce heat. That's usually why we do combustion reactions, is to make heat, to give to something else. Chemical cold packs often, probably usually, contain ammonium nitrate, and ammonium nitrate dissolves in water as an endothermic process. And because it's an endothermic process, it absorbs energy. Energy goes into the process. It uses up rapidly a lot of the energy around it. And so your skin, the water in the cold pack, whatever it is, the surroundings, get colder because that cold pack absorbs heat. The way that the ionic compound dissolves causes it to absorb heat, and that causes the reaction to decrease in temperature rapidly. So it rapidly absorbs energy, meaning that it gets cold. And that's also convenient to use ammonium nitrate because it's not like a dangerous chemical. So if you were to spill it, probably not that big of a deal as long as you're not drinking it. On the other hand, chemical hand warmers contain iron filings, basically just iron dust, and that gets oxidized in an exothermic reaction. It reacts with oxygen in the air as an exothermic reaction, and it produces heat. It releases heat. As a result, so it gets hot. Burning of natural gas is another exothermic reaction. So if you've ever opened an old pack of those hand warmers, sometimes they're duds after the best by date. Presumably the iron filings have already reacted with whatever trace amount of oxygen was in the pack, or you opened it maybe and didn't use it right away and it's just been sitting in a package, but it's been slowly reacting over time. All right, each of these processes is either endothermic or exothermic. We also want to indicate the sign of delta H based on whether it's gaining or losing energy. An ice cube melting, is that absorbing energy? Is the ice absorbing energy, or is it releasing energy when it melts? It's absorbing. An ice cube melting is absorbing energy. It's endothermic. It needs to gain heat to melt. So it's going to be a positive delta H. It's going from a solid to a liquid. And if we make this little one energy or one axis plot of the states of matter, Our lowest energy state of matter is solid. Our middlest stage of matter, middlest energy form of matter is liquid. And our highest energy state of matter is gas. So if we're going from a solid to a liquid, we need to gain energy. What about nail polish remover, acetone, quickly evaporating after it's spilled on skin? We've got a guess for exothermic. Any other guesses? What state is the nail polish in before it evaporates? It's in a liquid. And what state does it go to when it evaporates? It goes to a gas. So does it need to gain energy or lose energy to do that? It needs to gain energy. And the energy that it gains is from our, in this case, from our hand. It's the same thing that you feel when you put hand sanitizer on. The isopropyl alcohol or whatever alcohol they're using in there absorbs energy from your hand and evaporates, taking its energy with it and making you feel cool. So this is also endothermic. It's going to have a positive delta H going from a liquid to a gas. What about gasoline burning within the cylinder of an internal combustion automobile engine? Is gas burning endothermic or exothermic? Does it absorb heat? Does it release heat? Does your engine get hot or does it get cold? It gets hot, so that means it's gaining energy. Where did that energy come from? The combustion. So the combustion released energy to make your engine hot. Burning is exothermic. And so this is going to have a negative delta H. It's losing energy. Questions about those? Might just take some practice thinking about them before we get a grasp for them. Okay, at the molecular level, an exothermic reaction gives off thermal energy. Where does that energy come from? We know that internal energy is kinetic energy plus potential energy. If the energy was coming from kinetic energy, the temperature would drop because kinetic energy is related to temperature. So high kinetic energy at the molecular level is going to mean high temperature. Low kinetic energy at the molecular level is going to mean low temperature. And so if the kinetic energy were the source, the temperature would fall, and it doesn't. The temperature actually goes up in an exothermic reaction. So it's actually the source of the energy is potential energy. We're converting potential energy into kinetic energy, into thermal energy. So that potential energy of the way that the atoms are arranged, chemical potential energy, gets converted into thermal energy. And here's this feels counterintuitive as well. Weak bonds are broken. This absorbs a small amount of energy. I think this comes up again later, but breaking bonds absorbs energy. It takes energy to break bonds. So the opposite is also true. Forming bonds releases energy. That's the part that feels counterintuitive. So we form strong new bonds, and that releases a lot of energy because they're strong. again, I think this will come up again later. I think it makes sense, probably for most of us, that breaking bonds requires you to put energy in. You have to put energy in to break the bonds. And so I think it's easier to think about flipping that, to think about what happens when we form bonds. And that's releasing energy. So that's for an exothermic reaction. In an endothermic reaction, strong bonds are broken, you put in a lot of energy. Weak bonds form, you release a small amount of energy. Let's say that we have an endothermic reaction that occurs in a flask. What happens to the temperature of the flask? Does it rise? Does it fall? Does the temperature remain unchanged? What happens with an endothermic reaction? Where's heat flowing? Out or in? Looks like we're mostly signaling in. So this absorbs energy. When it absorbs energy, what's that going to feel like? Is it going to be cold or hot? It's going to be cold. So it absorbs energy, so it gets cold. Burning is an exothermic reaction. So like burning a candle, burning a piece of wood, combustion in your engine. Burning, famously, hot. That's exothermic. Exothermic is hot, so the opposite should also be true. Absorbing energy, or endothermic, is going to be cold. So this is going to cause the temperature to fall, because it's absorbing energy, it's taking kinetic energy and it's turning it into potential energy. When we're doing chemistry, we can do stoichiometry that involves delta H. This doesn't change a whole lot for us. It's sort of just like a one extra step thing that we add on. So we can calculate the enthalpy change, the delta H, for a chemical reaction, this Rxn. So the enthalpy change, delta H, for a chemical reaction, that's the sub Rxn, is also called the enthalpy of reaction or the heat of reaction, H for heat, that's nice. This is an extensive property. It depends on the amount that we use. We know that it's extensive because if I light a little pile of wood, it's going to be hot. If I light a giant pile of wood, is that going to be the same amount of heat or a lot hotter? It's going to be a lot hotter. So the amount that we use changes the amount of heat that's transferred. Typically, we calculate the heat of reaction for a number of moles as the reaction is written. So for example, with the burning of propane, C3H8 reacts with oxygen, forms CO2 and H2O. And this reaction, as it's written, has this delta H, this heat of reaction. It's negative 2,044 kilojoules. So if we burn 1 mole of propane, that's going to produce 2,044 kilojoules. If we burn 5 moles of oxygen in that reaction with the propane, it's also going to release 2,444 kilojoules. So the delta H, essentially we treat it like another coefficient. So we can select any two things that we want, and we set those equal to each other. But it has to be in moles. Just like our stoichiometry does. So this lets us convert between moles and kilojoules. So let's say that we have this following chemical reaction. We've got 2A going to form AA, or we could also rewrite it as A sub 2. So the A's are bonding together, forming a molecule. And we've got a delta H of the reaction of negative 51 joules. We want to know what's the heat What is the heat associated with the reaction of 6 moles of A? So we're starting with 6 moles of A. We are going to heat. Heat has units often of joules. Sometimes it's also calories. What are the two things that we care about in our chemical equation? What's the thing we're starting with? We're starting with A, so that's one of the things we care about. What's the other thing that we care about? Do we care about the A2? No, we don't care about the A2. Forget about the A2. So the other thing that we care about is the delta H. We care about the heat, the joules. So we're going to take those two things, set them equal to each other, and that's our conversion factor. So 2 moles A equals negative 51.0 joules. And that is our conversion factor. So this will let us go from 6 moles of A to whatever amount of heat. So the moles part goes on the bottom. 2 moles of A on the bottom. That cancels with the moles of A that we started with. Negative 51.0 joules on the top. So we do 306, negative 306 divided by 2, negative 153 joules. Wrong color. Questions? Okay, so the correct answer here would be C. The wording associated with is just saying, just give us the number, don't make it positive or negative, just whatever you get, that's the number that we want. Sometimes the wording for these questions can be like how much heat is released, and then it wants you to flip the sign. It's like if it was a negative, in this case, if it said how much heat is released, we would say 153 joules. So that can be confusing and frustrating. It really brings out the worst of word problems, or what we probably think of as the worst of word problems. Another example, ammonia reacts with oxygen according to the following equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of NH3. So we've got grams of NH3, ammonia to start. We want to calculate the heat. It's just saying associated with, so again, we're just going to, whatever the number is, we're going to put it. What are the two things that we care about in our chemical equation?
NH3.
We care about NH3.
The 906 kilojoules.
And we care about the kilojoules. So we're going to take those two things out, and that's our conversion factor for that step. We're producing 906 kilojoules of energy. That's what the negative means. We're releasing that much energy for every 4 moles of ammonia. So starting with our 155 grams of NH3, is there anything else that we need before we can plug this into our calculator and solve it? We need to convert it to moles first. So we're going to need a molar mass for ammonia, which is 17.031 per 1 mole of ammonia. Grams of ammonia cancel. The moles of ammonia cancel. and we should get out negative 2061.38 and some other stuff, kilojoules. We'll round it for 3 significant figures. So you should have one of these two answers. So it's a little change to the way that we've done stoichiometry, but also it's not really a change. We're just adding another thing that we can convert to instead of doing like moles of ammonia to moles of nitrogen monoxide or water. We're just adding, you can convert to heat instead. Let's do it in the opposite direction. What mass of butane in grams is necessary to produce this amount of kilojoules of heat, and also what mass of CO2 is produced? What are we given? What's our starting point?
1.5 times 10 to the 34.
Yeah, kilojoules of heat is what we're starting with, because that's what we were given a number for. The way that it's written, it might feel like we're trying to somehow find heat because that's put second. This frequently happens with word problems where it feels like it's written backwards. So we're starting with kilojoules of heat, and we're finding mass of butane in grams, and we're also finding mass of CO2 that's produced. So we basically got 2 problems that we're solving. So starting with our 1.5 times 10 to the 3 kilojoules, do we have something that relates kilojoules with butane?
The reaction releasing 2,658 kilojoules.
We've got the reaction with the delta H. So this has in it the delta H, which we care about because that's the amount of heat that we're starting with. That's the amount of energy that we're starting with. And it also has in it the butane and the CO2. So how many moles of C4H10 are produced for every this amount of kilojoules that's released? 1 mole. So we can put the heat on the bottom, and we put the 1 mole C4H10 on the top. That's butane. But is our prefix for 4 carbons, going back to our nomenclature. So that's how we would know that that's butane. We could also just name everything else and figure out process of elimination that C4H10 is our butane. So when we do this step, our kilojoules, I put kilograms, that's fun. Our kilojoules cancel. This would leave us with moles of C4H10. We need to get it to mass of butane. So we're going to need molar mass. Which should be 58.124. If you've forgotten how to do molar mass calculations, our friends in the STEM room, the STEAM room, our STEM ambassadors would love to review that with you, Jonathan and Liz. They should be in there, probably yapping, hanging out from noon to 5, Tuesday, Wednesday, Thursday. So go give them some work. Any questions about the way that we set this problem up? The number that we get out, the way that we've written this, is negative 32.8 and some other stuff grams C4H10. So that would round to negative 33 grams C4H10. Is that correct? Did we burn negative grams? No, we didn't burn negative grams. What could have happened that we got a negative?
The negative heat reaction.
It's from the negative heat of the reaction. We should end up with a positive, right?
Use absolute value instead of the negative.
We could absolute value it. That's what I would recommend for this. If we were ending up in grams, you can't have negative grams. We put the numbers in correctly. What we didn't do is the problem says to produce 1.5 times 10 to the 3 kilojoules. And this to produce makes that number negative. Producing heat is losing heat. Losing heat is a negative number. So one way that we can solve this is add a negative at the front, or we can also just think to ourselves, we can't have a negative amount of grams, so it must be the positive amount of grams instead. And that would also work. So I let us have that mistake intentionally to show us that this can happen to us. If you get a negative grams, probably you just forgot a negative somewhere, make it a positive grams. We can also do the same steps, but going to mass of CO2 instead. And for mass of CO2, we're going to 4 CO2. It's the same delta H. So our first step will be slightly different. We're going to have 4 moles CO2 on the top. And on the bottom, we're going to have the same negative 2,658 kilojoules. And we'll have a molar mass of 44.009 for our CO2. Mole CO2 cancels, kilojoules also cancels. We put numbers into the calculator. We should get out 99 grams after we round. Another way that you could have done this problem, you could have taken the grams of butane that you found, converted that back to moles with your molar mass, then done stoichiometry between the butane and the CO2, and then converted to grams, and then you get grams CO2. It will give you the same answer as long as you didn't round somewhere in the middle. Questions about gestures, jazz hands? So stoichiometry plus this one weird step, this one weird trick. We did calorimetry. We've done calorimetry. Now we're finally talking about it. So delta H of the reaction for many aqueous reactions can be measured in a coffee cup calorimeter. We've done this. Typically you take either 1 or 2 nested foam cups for insulation. The styrofoam cups are very good at insulating, part of the reason that they've been used for coffee cups for a long time. They're also really bad for the environment, which is why we recycle them semester to semester. If this is open to the atmosphere, then it's at a constant pressure, and our Q of our solution is going to equal the mass of our solution times the specific heat capacity of our solution times the change in temperature. So if we know the mass, if we know the specific heat capacity, and if we measure how much the temperature changes, then we can figure out how much heat the solution lost, which would be the amount of heat that was produced by the reaction. And under constant pressure conditions, Q equals delta H. We talked about this. It would be a long time ago now, but we did talk about this. And then typically to get delta H of the reaction per mole, so that we can put it at the end of our reaction if we wanted to, we divide by the moles that reacted. So this might look something like this. Wow, a block of text. So we set up some information. The addition of hydrochloric acid, HCl, to silver nitrate, AgNO3, precipitates silver chloride, AgCl, according to the following reaction that we've got here. It is balanced. We've got one silver on both sides, one chlorine or chloride on both sides, one hydrogen on both sides, one nitrate on both sides. There's no coefficients because they're all +1 or -1, and it's a double replacement reaction. We are told that when 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar hydrochloric acid, the temperature rises from this value to this other value. We want to calculate delta H of the reaction as written. We're going to use 1 gram per milliliter as the density of the solution, and C sub S of 4.18 joules per gram degree Celsius as our specific heat capacity. So we've got a whole lot of information. Let's unpack it a little bit. We have some conversion factors, some things that were given at the end. 1 gram per milliliter is the density of the solution. That might be important. D equals 1.00 grams over milliliters. We are also given the CS, 4.18 joules per gram degree Celsius. What are we finding?
Heat capacity reaction.
We're finding the delta H of the reaction. The heat of the reaction. And this is going to have some value of joules, and it's secretly going to be per mole reaction. There's always that secret per whatever the coefficients are, moles reaction on our delta H. So that means we need some amount of energy. We need some amount of joules. We can get joules. We can calculate joules with an equation. Q equals mc delta T. We have C, because we were given C. Do we have enough information to get delta T? What's delta T? It's TF minus TI, and we were given temperature values, 23.4 degrees Celsius, 24.21 degrees Celsius. Those are our TF and our TI, but in the opposite order. So our delta T, 24.21 degrees Celsius minus 23.40 degrees Celsius. Our change in temperature is 0.81 degrees Celsius. So now we've got our delta T. We've got our C. Do we have M? Were we given any mass values? In density, so we have to convert. We would need milliliters to get to the grams. We've got 50 milliliters of each of the solutions. So together, that's 100 milliliters of solution. It's not going to be exactly 100 milliliters of solution because the way that volumes add, it might be slightly different. But we're just going to assume that it's exactly additive. So we've got 100 milliliters of solution. If 1 gram is equal to 1 milliliter, then 100 milliliters turns into 100 grams. Now we've got mass, we've got C because we were given it, we calculated delta T. So we can calculate our Q. It's 100 grams times 4.18 joules per gram degree Celsius times 0.81 degrees Celsius. So 100 times 4.18 times 0.81, we get 338.58. This will have two significant figures, and the units are joules. Is that our answer? It's not our answer. Why is it not our answer?
That's just the heat transfer solution. Of the reaction.
It's just the heat. We need the heat of the reaction, which is on a per mole basis. How many moles did we use? We get to invoke a little bit of solutions. So we had the concentration specified for our solutions. This is also a relatively involved version of this problem. Don't expect to see something like this on an exam unless it's worth 6 points probably. So we were given some bonus information. We are given concentrations. Conveniently for us, it's the same number of milliliters and the same number or the same value for concentration for both of our reactants. So we can choose to just use either one. That's a nice thing. Do we remember what the big M stands for here? It's not the big M that we'll see on the exam today. It's a different big M.
Molarity.
Big M here means molarity, and molarity is moles over liters. The big M that we'll see on the exam today is molar mass. Different from this. This big M is for solutions, and it's molarity. So we can calculate moles using this equation. So moles is going to be equal to molarity times liters. You could also use the triangle thing, that little shortcut that I've showed you before. It also works for density. So moles is molarity times liters. The molarity is 0.100 big M. Our liters, we have to convert. I'm going to just assume that we can do that to save time. Molar times liters equals moles, so 0.1 times 0.05, 0.00500 moles. Almost there. We take our joules, we divide it by our moles. And that's a really big number. Try to tactically shrink some stuff here. Delta H of the reaction equals, we'll call it Q over N. So heat over moles. 338.58 joules divided by 0.00500 moles equals we skipped a step. I'm going to show us how we can get the right answer. I'm going to try to show us how we can get the right answer even though we skipped that step. The number that we get out is 67,716 joules per mole, we could make that 6-7 kilojoules per mole. The number is correct. However, did the temperature of our solution go up or down? The temperature of the solution went up, which means that it gained heat. That means that it would have gotten the heat from somewhere. The somewhere would have been from the reaction. The reaction must have given the heat to the solution for the temperature of the solution to go up. If this is a positive number, that means the reaction is absorbing energy, which means it would be taking energy from the solution, so the temperature should be going down. So for it to be giving energy to the solution, it would have to be what? Positive or negative? Negative. It would have to be negative. So that's a way that we could logic our way into getting it as a negative. The thing that we forgot was this part. The Q reaction equals negative Q solution. I'm adding in as black text the stuff that we forgot, the stuff that would have been helpful to label. The Q of the solution is what we calculated, and the heat of the reaction uses the Q of the reaction. Q solution is the negative of the Q of the reaction. So that's the step that we missed, and that's what would give us a negative at the end, which is what we should have. Questions about any of the many parts that we covered there? We did some solution stuff, we did some heat stuff, we did some flipping Q. Okay. Conceptual question. The same reaction with exactly the same amount of reactant is conducted in a bomb calorimeter. Think to yourself, what is a bomb calorimeter? Do we remember back to multiple weeks ago what a bomb calorimeter is? It's also done in a coffee cup calorimeter. That's the one that we were just looking at, the one that we did in lab. What's different about those two things? We might want to think to ourselves. In one of the calorimeters, the Q of the reaction was negative 12.5 kilojoules, and in the other, Q of the reaction was negative 11.8 kilojoules. Which of those two values was obtained in the bomb calorimeter? Who remembers what a bomb calorimeter is? What's special about a bomb calorimeter? So a bomb calorimeter has a sealed container. It has constant volume. Does the coffee cup calorimeter have a sealed container that causes it to have a constant volume? It does not. It has constant pressure. But the gas can expand. It's not really a but, it's more of a just it can expand. How might gas expanding be relevant to energy? Do we remember anything about gas expanding, gas changing its volume, and energy? if the gas is expanding, what is it doing? Is it expanding into a vacuum? It's expanding into the atmosphere. So if it's expanding into the atmosphere, what's happening to the gas that's around it? It's being moved, right? The gas in the coffee cup calorimeter is causing the other gas to move. When you push something, does that take energy? Yes, that takes energy. So we're doing some pressure volume work. So the coffee cup calorimeter expands, meaning that it does pressure, volume, work. When you do work, do you gain energy or do you lose energy? You lose energy. So it loses some energy. So would we expect it to have more heat or less heat if it's used some of its energy as work? Less heat. So the coffee cup calorimeter is the smaller value, which means that the bomb calorimeter is the bigger value. So all change in energy is heat. Doesn't lose any to pressure volume work. This is what I'm talking about with pressure volume work. Work equals negative P delta V. Will you be using that on the exam? This is the question that I forgot to take off the exam, by the way. Question?
No, I'm just reacting very low.
Okay. I'm going to slide away from that, and we're going to pause for a second. We are so back. There are some relationships involving heat of the reaction. So the change in enthalpy, the change in the delta H, is for one particular reaction as it's written. If the reaction changes, the heat of the reaction also changes. So there's a couple of things that we can do. If the chemical equation is multiplied by some factor, the whole thing, the delta H is also multiplied by the same factor. So, for example, A plus 2B goes to C. If we double the whole thing and give it to the next person, all right, we double it. Now there's a 2 in front of the A. The 2 in front of the B turns into a 4. The 1 in front of the C turns into a 2. And the delta H of this is twice the delta H of the first one. So if you double it, double the heat. If you cut it in half, cut the heat in half. That's one of the things we can do. You can also do it with not just doubling or tripling or cutting it in half or cutting it in a third. Any numbers that you want to put in front, you can also do it with those. So you could do 5/16. I don't know why you'd ever do that, but you could if you wanted to. If the chemical equation is reversed, then delta H of the reaction changes sign. So if it absorbs heat in the forward direction, in the reverse direction, it releases heat. If burning something releases a bunch of heat, then unburning something would absorb a lot of heat. And we also have Hess's law. Hess's law says that we can add up reactions and add up the heat. So adding reactions together adds the delta H's. When we do this, when we add the reactions, we need to cancel things that are on both sides. Sort of like when we're adding stuff together for our redox reactions. When we're adding our reduction and oxidation half reactions together, we cancel stuff out that's on both sides. We have to do that for Hess's law as well. Hess's law basically just says if we can do something as a sum of steps, like if we can do it like I drive to the grocery store, then I drive home from work to grocery store to home. If I know the amount of time it takes for each of those driving trips, I can add those together to get the total trip time. That's sort of what we're doing here, but it's for heat transfer instead. So what this lets us do as chemists is we can figure out the enthalpy change of a reaction, the heat of a reaction, without directly measuring it. Like if it's difficult to directly measure the way that one reaction occurs, we can do it as a series of steps instead. We actually did a Hess's Law lab, so we might have already done some of this. If you haven't done the post lab, that's fine. You can still turn it in late because I forgot to cover it. What this requires us to do is we have to manipulate reactions, so maybe doubling, tripling the coefficients, flipping them left and right, and then combining them with other sets of reactions. Then we'll add those up, and that's our delta H. Let's look at some specific examples that let us look at these rules. We want to consider the following reaction. 2A plus B goes to C. This equation as written has a delta H of 122 joules. What's the delta H for 2C going to 4A plus 2B? What are some changes that we made from our original chemical reaction to this new chemical reaction? What's one thing that we changed? We flipped it. We flipped it left and right. What happens when we flip something left and right? What does that do to our delta H? It flips it how? It flips it, makes it negative. So we flip it, flip. Now it's C going to 2A plus B. Delta H of the reaction is negative 122 joules. Do we have the new reaction? Or do we have something different still? Still different. What changed after we flipped it? What else do we have to do? The whole equation's doubled. When we double the equation, what does that do to our delta H? It also doubles. So now it's 2C goes to 4A plus 2B, and our delta H of the reaction still negative, but now instead of 122, it's 244 joules. So D would be the delta H for this new reaction. So for solving stuff like this, how did we change from what we were given to what we ended up with? You can flip stuff, you can multiply it up, you can divide it down. Knowing how these two steps work is crucial for setting up Hess's Law experiments, Hess's Law problems, which I would have given you on this exam, but we didn't cover it. So I remembered to take that off at least. Okay, we want to find delta H of the reaction for this reaction using these reactions with known delta H's. So we need N2O on the left, we need NO2 on the left, we need NO on the right. There's a bunch of different ways that we can go about doing this. The way that I solve these is I look for, do we have equations, where do we have equations that have these things in them? Our first equation, we've got NO, we've got O2, we've got NO2. Do we need any of those for this reaction? Do any of those match? Do we have O2 in our reaction? No, no O2 in our reaction. Do we have NO2 in our reaction? Yeah, we have NO2 in our reaction. Where's the NO2 on the reaction? It's on the left side. And in here, it's on the right side. The NO here is on the left side, and here it's on the right side. So what would we need to do to get the chemicals to be on the right sides from this reaction? We would have to flip it. So we're going to flip this one. And that turns it into 2NO2 goes to 2NO plus O2 delta H 113.1 kilojoules. Shoop. 113.1 kilojoules. So some issues is that I am having my brain glitch. Okay. We also have the O2 though, right? We don't want O2. So we need to get rid of the O2 at some point. We're also short one NO, and we don't have N2O. Do we have N2O in either of our other equations? Do we have it in our second or third equation? N2O. Where's N2O? It's in the third one. So we have N2O in the third one. So we are probably going to need to use this. This is the only one that has N2O in it, so we're going to have to use this one to get to this equation. Do we have N2O in anything else? Do we have it in our second one? I don't see any N2O. We don't have it in our first one. I don't see any N2O. So if we've got two N2O here and we want one N2O, what do we have to do to this reaction? Divide by 2. So we divide by 2, and that'll turn it into N2O goes to 2N2 plus 1/2 O2. What happens to our delta H? If we divide the reaction by 2, what happens to our delta H? It also divides by 2. So negative 163.2 divided by 2, it's negative 81.6, still kilojoules. Okay, let's see what happens if we put these two things together, just to simplify things in case we're having trouble tracking all this. So we've got 2NO2, I don't know why I changed colors, 2NO2, I'm going to write the N2O in front. So we've got the N2O, we've also got the 2NO2 on the left. On the right side, blue arrow, we've got 2NO plus 2N2 plus 1.5 O2. Pause. Unpause. We haven't used our second equation yet. Our second equation has N2 in it, and that we could use to cancel out the N2 that we've got left over. It's also got some NO in it, and we need some more NO. Right, we've got 2 NO, we need to get up to 3 NO. If we add it as is, that would give us 4 NO. So that can't be right. If we add it as is, it's also going to be 1 O2 on the left. That's not going to cancel out our 1.5 O2 on the right. So we need to either reduce the amount of O2 that we have on the right, or we need to increase the amount of this that we have. If we multiply this by 1.5, that would also multiply this by 1.5, so there are O2 cancels. We would end up with 3 NO, then we would end up with 5 NO on the right. So that can't be it. So we have to reduce the amount of O2 that we have and what we missed, or what we can do as a second step, we have to divide this by 2. So we also have to divide it by 2. And that changes some things. We're also going to divide that delta H by 2, updating our things. Our delta H would be this. I'm being lazy and not writing in doing the thing in the calculator. This is what we currently have for our delta H. What fun. Now, if we add this second one, our O2 what is happening? We love having a meltdown. Oh, what's happening is I forgot to delete that too. Okay. Now, if we add reaction 2, we've got an N2 on the left, we've got an O2 on the left. That would cancel out with the N2 and the O2 on the right. We've got 2 NO. That would add to the NO. We'd get 3 NO. I don't have a good formulaic way of solving these problems. It's just pure problem solving skills. Can you add stuff together? How can I change stuff to get it to work? Historically, people don't like these questions. I have typically given easier versions than this on the exam. So we're just going to do that as written. N2 plus O2 goes to 2 NO. The N2 cancels, the O2 cancels, and we add to this our 182.6 kilojoules. The answer is 157.55. We'll round that up to 0.6 kilojoules. For next time, we'll start off with this other Hess's law problem that's arguably simpler. Arguably. Any questions?